Good evening, everyone. Thank you for listening to me. And at first, some of my slides has 20 font size, so the audience near the back door, please come front a little bit, if possible. Okay. I would like to talk about how to leverage multi-GPU acceleration for speeding up the workflow between Elastic Stack and Splunk. Recently, everyone talked about the GPU for image processing, GPU for deep learning, but it's not everything. So I'll tell you what in this presentation. I will also introduce 3 years operational experience in deploying multi-GPU accelerated monitoring system on the huge academic backbone network, which is called the SINET in Japan. SINET is a backbone network for more than 800 research institutions and universities. That was really awkward mission. So the outline is divided into 9 items and 3 blocks. At first, let me introduce the overview of pipeline of Elastic Stack, GPU, and Splunk. Okay? And then let me go slightly back to past situations and the pitfalls. And the third one is the core topic of the first block. This is about strategy of parallelism for unpredictable. The key point is here that the session data stream is unpredictable. This is not scientific computation. This is all about engineering for people. And the fourth one is, let me introduce design philosophy a little bit. And the fifth one is Floorplan and configuration. And the second block is divided into 3. Huge pagination of Elastic Stack and the direction discrimination, which is distinguish ingoing traffic from outgoing. And the final one is histogramming, which is very common operation. But in the case of copying with billion of session data stream, the problem is become more difficult. And finally, let me conclude this talk with some impressions. Okay, let me take a brief look about the pipeline. Our pipeline is composed of PA, firewall, Logstash, Elasticsearch, GPU, and Splunk. We have set acceleration module at 3 points: retrieval, discrimination, and histogramming. And the background and the bottlenecks from 2016 September to October in this year. Maybe, as you already know, East Asia is under disturbing situation. I'm not a journalist, so I'm not going to go deeper in this topic, but in early 2010, there's many information breaches in Japan about universities. So this is a top-down project from government, ministry, and universities. And unfortunately or not, SINET connects various kinds of research facilities like this. And these research facilities attracted APT people. And the main topic is this. It's all about large computation time. For example, to handle session data stream from PA 7018 100 gigabyte for 24 hours, the randomly generated in this talk. This is the catastrophic situation for us. Data dump took 1,600 minutes. And the discrimination, this is basic operation, took 700 minutes. And the histogramming, it's table, it took 470 minutes. Let me illustrate these three pitfalls on the pipeline. First one is about huge pagination. It really takes a long time. And the second one is massive bit masking required by the traffic discrimination. Bit masking on the multi-core CPU using C++, Boost or C++, took a long time than we expected. And the final one is billions by milliseconds, means the histogramming of huge session data. On server side, the Splunk and the Elastic Stack is slow because it's memory intensive. So the histogramming on server side using the analytics module of database, it took more than 400 minutes. Surprisingly, we can achieve the reduction to 12 minutes. In this point, let me recommend the effectiveness of GPU. The problem is simple. How can we reduce unreasonable computing time by multi-GPU acceleration? Is it right to pronounce the multi or multi? Multi is multi. Okay. Let me introduce the design philosophy for network engineer, not data analyst. Data mining is plastic art. This is said by the professor somewhere in the United States. Data mining is often considered in terms of location and extraction of pieces of information, but this metaphor is entirely wrong. What he is saying is that the false positive is problem. And actually, the cost of evaluating false positives is more expensive than the computing time itself. So the world we are living, the crafted filtering is the first priority. In a nutshell, subtraction is more important than naive addition. Okay, let me go on to the strategy of parallelism. The uncertainty is the fact of network traffic, as we already know. Sessions are unpredictable, so the dynamic allocation is useful in this case. Session in the word of, I cannot pronounce it extremistan. This is quoted from the book of Nassim Nicholas Taleb. The sessions are not homogeneous. Some are large, small, short, and long. So we cannot use static scheduling as is in scientific computing. In the case, the amount of processing time for each chunk is different or even unpredictable. The task decomposition is really useful. This is a basic diagram from textbook about the classification of decomposition pattern. Surely we use pipeline, and we adapt task decomposition on multi-GPU server. Dynamic allocation for unpredictables. The first thing we have discovered is that session data are not stored evenly in each shard of Elasticsearch. If you have a case where the computation time are variable, are different or unpredictable for each chunks in the structure, the dynamic allocation scheme is useful. If your data isn't organized in regular pattern or unpredictable, you should consider the dynamic scheduling scheme. Surely there's some overhead associated with dynamic allocation scheme, but the benefits will be more than the overhead of load balanced execution. This is a core idea of this presentation, dynamic allocation associated with merge GPU. The concept is really simple. The GPU accelerate consumer threads, that's all. But it's really powerful because in this case, the number of pieces of work, such as JSON, CSV, is 128, which more than 8, which is the number of GPUs. This is a code fragment of this scheme. This is simple. Please line 8, the program calls reduction kernel of GPU, and the GPU switch to the GPU ranging 1 to 8, and then call back. This is another constraint of the layers of parallelism. This is also from the textbook. The important thing here is choosing appropriate level of parallelism is important. The 4 layers is specified by the memory usage constraint, the pipeline completed. At first, we have adapted process level with, for huge pagination with 128 processes. And then we use dynamic allocation as a point B with 64 threads and 8 threads. Finally, we use machine level instruction for constructing the cluster of Splunk with 6 indexers. And the Floorplan and the cluster configuration. Let me illustrate this briefly. We have 2 teams. We are working with government, and one is academic officers. Their term is often a few years, so some are often newbies about IT security. Another one is SOC team with more than 3 years experience. They are responsible for prioritizing alerts and analyzing incidents. Their requirement and complaints is that the university is saying don't touch your LK stack because aggregation is memory intensive. So this is why we have separated analytics from Elastic Stack. And the SOC team is interested in Splunk, as is usually. For being proactive, they are interested in change points. So this is why we have introduced Splunk with feature-rich commands. Another difficult thing is Floorplan. Unfortunately, we had to cope with billions of session data stream with only 8 rack spaces. I was expecting that it's a good chance to cope with clusters such as Spark and Hadoop, but it was impossible. And GPU is impressive because it is estimated that it could deliver performance up to CPU-only configuration at 1/10 hardware cost and also in cooling cost. This is a brief description of a cluster. It is very common to the audience. We have 3 log stashes, 3 master nodes, and 9 data nodes. On Splunk, single search head, one master node, and 5 indexers. This is also a common description about the Elastic Stack. It is designed for scaling horizontally, not vertically, as the engineer of Elasticsearch is saying. And please skip this slide because it is common to use file bits to receive the input from the file. And Splunk is time series indexer. We really love stream stats. Stream stats is really useful for change point detection. And this is how our cluster is constructed. The key point is here, geofilter is the geostats plus stream stats. We divide the data into some indexes according to the area, Asia 1, Asia 2, US and EU. I'm not an essayist, but please say something about this briefly. The Treaty of Westphalia is over. Although I'm not European people, but I agree with that. As long as I observed basically the properties of countries should be assured and protected, but the contract is being collapsed. It's a very disquieting situation. In a nutshell, we cannot control the traffic from abroad by physical border control. More important thing is this, the data in this talk is randomly generated. All programs and data is recorded in my GitHub. Please see it if you are interested. Okay, please go on to 3 pitfalls. Huge pagination without scoring. This is equivalent to all data dump in SQL database. Scroll API is designed based on the pagination. Pagination is kind of snapshot, and divide the snapshot into some pieces. We often need more and more data to render on a page to analyze in the backend, as is usual in browsing web pages. But different is that the functionality of scan scroll is that which is needed frequently is 2 purposes: the returning large set of data to analyze and re-indexing. This is okay. We are at this point, the first phase of the pipeline. And please let me illustrate very briefly about Elasticsearch. There are 3 nodes: client, master, data nodes. Data nodes is important because it's for the data. And this is core idea of multiplex scroll API. As we know, index is divided into shards. Moreover, shards can be split into several slices. And when we invoke the scroll API, each process has a slice over multiple shards. But okay, horizontally. So if we have n processes for each process, and each process queries for n shards, in total, n time m queries are issued. This is a result of speeding up. We have achieved about 10 to 12 times speed up with the multiplexing of 128 processes. Speeding up much depends on the performance of the cluster of data node. If we succeeded to write a very good program on client side, It could be not effective because most of the performance depend on the spec of server side. This is a summary. In our experiment, the optimized number of chunks is 128. It's less than the threads running on the modern CPU. About 64 is a little bit too many. And actually, it could be 32. And the number of GPUs NVIDIA DDX1 could have is 8. So task decomposition is powerful. Because there are many more pieces of work than threads. And the second pitfall is about bottleneck. 2. Sorry, the 12 minutes remaining 20 minutes remain. Okay. Pitfall 2 is about discrimination of ingoing or outgoing traffic. It sounds very naive operation, but it's really important because when we receive the data stream from firewall, there's a label of ingoing or outgoing. So the first thing we should do is to append the label of ingress or egress to each session data. In this case, the bulk masking is really powerful. This is how direction discrimination works. The problem here, the discrimination requires the huge amount of iteration. In this case, bit masking, I cannot calculate the very large number. And the bit masking, does everyone know? Bit masking is really heavy operation. Even you use a boost or C++ container, the bit masking is really heavy operation. If you are to adapt the conventional techniques such as loop division or using OpenMP, the catastrophic situation will be coming. Actually, just for bit masking operation, it took more than 700 minutes. It's just for appending label, ingress or egress, to each session data. It took more than 700 minutes. In this case, GPU is not useful. GPU cannot run between Elasticsearch and Splunk. But we have adopted CUDA Thrust. Thrust is STL-like library for higher level approach to GPU. The important thing here is the functor or bitwise operation with transformation is possible. Simple and elastic. There is a common phrase that the engineer who cope with parallel computing is saying many times. Simple and elastic is important. Surprisingly, only about 10 lines evades tidy parameter selection in loop division or data decomposition. Can you believe it? Actually, this function outperforms the sophisticated programming of OpenMP or Silk or something like that. It's really powerful. Okay. What would I like to say in this slide is that Axe is basically for removing what is disturbing from it rather than naively adding to it. Reduction is really important. Some people say GPU is expensive, that GPU is just a luxury. Okay, we try it for playing. But I want to say that in this case, GPU is essential for driving pipeline to cope with billions of session data. Okay, let me go on to the final pitfall. Histogramming in milliseconds. We have adopted map reduce and tiling. Map reduce is really common technique that since the researchers from Google published a paper, I don't remember, maybe 2004, about map reduce. Map reduce is originally came from Lisp programming language, and procedure is simple. Usually the fine reduction, cost reduction, but the map reduce is really application specific. If you cope with billions of session data stream, the map reduce become extremely difficult. We are at the final phase. Actually, the time histogramming on Elasticsearch or Splunk, it took more than 476. It's very unreasonable computing time. But with GPU, we can reduce it to 12 minutes. Tiling is a key concept here. This is the most important slide I would like to inform the audience. This is a combination of CPU and GPU. I want to say that the CPU and GPU is complementary. Tiling is a design pattern for dividing procedure into several steps of a suitable granularity. The suitable granularity is important here. In general, tiling consists of the applying multiple process for each step instead of executing each process on the whole problem one by one. So in this slide, we have adapted the pairwise reduction for the upper side, and we have used merge scatter pattern for the lower side on this figure. Pairwise reduction, it looks very naive. It looks very slow, but it's powerful in this case. In pairwise reduction, chunk has only pairs of 2 elements. And the thread sums those 2 elements to produce a partial reduction. Reduce by key performs the reduction operation on key value pairs. This function takes 5 arguments. Key, starting of key, end of the key, and beginning of the result, and endpoint of the result, and so on. Merge scatter pattern is traditional way to compute histograms introduced by Intel TBB. Now, in merge scatter, the elements are combined by associative operator, which is plus in this case. Outputs which collide implementing a scatter pattern are combined with an associative operator. Okay, let me introduce a brief comparison result between merge scatter and pairwise reduction. In a nutshell, when we cope with billion session data, pairwise reduction is faster. Because the density of time series data is increasing, the pairwise reduction, which is naive operation, but is getting faster. This result is architecture or operating system result independent. So if you're interested, please try this command. You could get similar result to this slide. The conclusion is that the GPU and the CPU are complementary because the CPU is slow when CPU is executing merge scatter pattern. But at the same time, the currently highly concurrent container, which drives merge scatter pattern, only an effective and reasonable way to share data among multiple threads. This is called fragment of merge scatter pattern. Please see the line ranging 10 to 12. On this part, the program inserts the result into hash map. I guess this is the only way to share the data among multiple threads. This is the histogramming with merge GPU acceleration. The architecture is simple. The pairwise reduction in nature is designed for the execution is multiple GPU. This slide implies that when you execute merge threading, I really recommend the merge GPU. Because this is a comparison between the single and 4 GPUs. In worst case, the single GPU is more than 25 times slower. This is awkward. Because the Thrust API is fully asynchronous, and maybe kind of lock contention may have been occurred inside the GPU device. Surely you can improve it by using stream in CUDA, but in any case, single GPU can hardly handle no more than the 36 gigabyte session data. This is a result of speeding up with merge GPU. 384 minutes speed up. This is about merge threading rather than merge GPU, but it is estimated that for copying with more than 700 session data stream, merge GPU can speed up the histogramming by ranging from 400 to 500 minutes. This is my insights. GPU is going to be more and more effective. It's a simple reason. There are many statistics and estimation about the data explosion. Many people say that for the next decade, the universe of data will be exploding and blah, blah, blah. But the sure thing is that 24 hours is always 86 millions and 400,000. that this means data density per 24-hour will be increasing as long as we live in Earth. Okay, let me conclude with some impressions. Okay. We have succeeded in total about 10 times faster by using multi-GPU acceleration. We use huge pagination for data dump to reduce 1006 the long computing time to 132 minutes. At the second phase, we have succeeded to reduce the computing time of discrimination from 704 minutes to 174. As a final phase, we have reduced the histogramming computation time from 476 to 12 minutes. GPU acceleration on the go. And this is the lessons learned from our operational experience. This is somewhat exaggerated, but this is from a paper from Google. They are saying that it turned out that algorithms such as k-means, recurrent neural network, and anything is okay, using a huge data set with a trillion items can be highly effective in tasks for which the algorithm using a sanitized data set with only millions items is not useful. This is unexpected for me because if an algorithm cannot work with a training set of less than a million examples, intuitive conclusion, maybe it cannot work at all. What I would like to emphasize is that choosing appropriate level of parallelism is important. Did you get that? And the final impression is this, that I like Shakespeare so much. I like this phrase. I like this phrase really so much. I would like to say that subtraction is more important than addition. Everybody is saying that visualization is important. The data mining is important. But actually, in the case where we stand on huge backbone network, what we should not visualize is more important. This is the simple that machine scales, but human cannot endure such a huge traffic stream. Okay, let me conclude this talk. I have reported the painful operational experience in standing huge academic backbone network. The summarized concurrency, huge pagination, bulk bit masking, and tiled map reduce has been introduced. I would like to emphasize that multi-GPU acceleration are essential for improving the workflow between Elastic Stack and Splunk. Okay, thank you for listening. Thank you for listening to me. That's all. Appreciate it.
Does anyone have any questions? Going one. Oh, please.
management?
Okay. Thank you for the question. This is a critical point to this talk. Actually, I have tried, but I couldn't. So I'm trying. But what I can say is that OpenMPI is good at data decomposition, but that maybe it wouldn't be effective so much about the case of handling the session data, which is unpredictable, of which size is different. Thank you.
Any more questions? I'd like to thank Ando for sharing his discoveries, and let's give him a round of applause.
Appreciate it.